Okay. Good evening, everyone. Celso Batalha, Evergreen Valley College, and this is Astronomy 10 Intercession in the last week of class. Today we had a midterm 3. Tomorrow I will open up midterm 3 so you can get a second shot. You're not going to see the same questions, but you know how they go. You can attempt to get a better grade. Um, so this is on Tuesday, so a second attempt of midterm at midterm 3. Now on Wednesday we have a makeup exam. The makeup exam I will not be proctoring face to face. So you have to try using Google Proctorio extension, or if that is not an option, I can try and see if the tutoring center is going to be open and I can have somebody assisting you, but you have to communicate with me. I'm assuming you can do that, but if it's not the case, let me know. That's for Wednesday midterm. In fact, it's a makeup exam. So the makeup exam, the way it goes, it works as a replacement of your lowest score in midterm, any of the three midterms, in case your makeup exam grade is higher. Um, as I explained in an announcement I sent yesterday, I think, is the same thing as putting three midterms and makeup and take the three highest score of these four midterms. So this is going to be on Wednesday, and then on Thursday is final exam. And again, final exam has no repetition; it's just one shot. I will open the final exam on Wednesday at noon, so you can do using Proctorio extension if you want it. So you're gonna have one day, 24 hours, because on Thursday noon I'm closing because I will be working on grades in the afternoon. Okay, so I will be um, proctoring the final exam face to face at Evergreen, room SA 114 at 10 o'clock as always. So if you want to do with me, so I will be there. Okay. Do you have any question regarding this last few days of class?
Yeah, for the final exam, so we're allowed to take the final exam on our computers at home. We don't have to go to school.
No.
Oh,
I
okay.
mean, yes, you can do it at home. You don't need to
Oh,
be in the
I thought
school.
it was like mandatory or something,
It
so
was.
I
I
thought we
mean,
were able to go.
okay. What is mandatory is to have the exams being proctored, right? And up to
Okay.
last fall, I didn't have the Google Proctorio extension available, which I have now. So now you guys can use that as a proctoring agent, and you are fine, and we are complying with the state laws. What the state don't want is that students do an exam without being supervised. That's the whole point. So
Okay, thank you.
yeah, so you can do it at home. And again, I give you 24 hours, beginning on Wednesday at noon and closing Thursday at noon. Okay.
I
Okay. So
also have a,
yeah, yeah. Go on.
but it's about the midterm today.
Yes.
Jeff, I was on here last week about needing an access code for my midterm because it wouldn't let me do it. And I had the extension and I was using Chrome and nothing was working. Like it wouldn't work, so you gave me an access code.
Yeah.
It
Can,
didn't
can
exactly
yeah. Can you talk
this.
to me after this talk? You haven't done the midterm 3
Yeah.
yet, right?
Do I just wait until 8 or so?
Yeah, I can't do now because I'm in the middle of a class. Yeah.
Oh,
Yeah. Sorry about that.
it's in.
Okay.
I'll join back then.
Okay. Sounds good. Yeah, why don't you email me? When you have these situations, you have to email me because there are so many little things going on in this course, and I can't keep track of everything unless you guys communicate with me. So if you need
Okay.
anything that's not being provided to you, you have to let me know, and then I will take some action. But if, don't expect me to remember things because I will not.
Okay, sorry.
All right, sorry about that. Yeah, so if you want, if you need to do something now, you can't stay in the chat room. Just send me an email now, and when I'm done, I'm gonna check, and then I will do whatever that is need to be done so that you can have access to the exam.
Okay, thank you.
All right. Okay. So if I can move this around, you guys can see my screen, right? Yes, you can. So I have a bunch of pictures here of galaxies in general, and we we initiated this course with a concentration on objects we can see with our unaided eye and paying special attention to the type of motions we can witness on a daily basis or in a yearly basis. The type of motions like day and night and rising and setting of stars and constellations and planets. But on a larger scale, we also focused on Earth revolution around the sun and the different seasons, the causes of seasons. But that was the astronomy related to what we think astronomy is to identify stars, to understand causes of apparent emotion. That was the first week of class, the night sky. And then we move on to study stars and and how stars are formed and what are the main roles of stars in the universe and one of these topics that come clearly is the fact that stars are responsible for creating most of the atoms we need for our survival. Certainly, hydrogen and helium, those atoms. Helium, not so important for us, but hydrogen is in water. It's a very important element. Hydrogen, helium, some lithium, and beryllium, these atoms were formed when the universe came into being, into existence, 13.7 billion years ago. And they are the result of Big Bang, basically. But most of other atoms, they are manufactured inside the stars. And when we studied stellar evolution last week, we tried to bring this aspect of stars to your attention so that when you finish this course, you look at the stars out there and then you feel a sense of reverence and connection because without past generation of stars that no longer exist, without them we wouldn't be here because our body is made of magnesium, zinc, iron, we have silicon, we have all kind of atoms and elements making up our cells like carbon, and they were manufactured inside stars. And when our solar system came to be formed, all these atoms were aggregated to our system and then later on to the process we call life. And here we are basically. But now, in fact, Friday, we initiated a new subject, and that is the subject we call galaxies. And the first galaxy that we studied was the Milky Way galaxy. So I will go over Milky Way galaxies and its main topics, and then discuss galaxies in general. But what galaxies are, as we saw in chapter 1, the first chapter we had in our course, galaxies are group of hundreds of billions of stars held together by gravity force. And these pictures here show different types of galaxies. So you see, these galaxies have a center part and has very clearly defined spiral arms. Same thing here. See that? Has a bulge and has very clearly defined spiral arms. Whereas if you look at this galaxy here, you don't see the spiral arms clearly, maybe because of its orientation, the angle upon which we are observing the system, but we do see a very clear and bright bulge, and also this dark lane that indicates some distribution of dust along the galaxy. More spiral arms here, another galaxy, spiral galaxy. So you have a bunch of spiral galaxies here, and what call their attention, what make them unique, is the presence of spiral arms we can easily outline. Look at this beauty over here. Now let's take a look at different types of galaxies, like elliptical galaxies. What's the difference between spiral galaxies and elliptical galaxies? Elliptical galaxies, they are somewhat different. So see, they have some smooth distribution of light from the bright bulge, and the brightness diminish outward to the edge of the galaxy. Same thing here, same thing here, and same thing here, although you can see some dark lanes in here. So elliptical galaxies do not show, this is a spiral galaxy as well as this one. So spiral galaxies are different from elliptical galaxies. Elliptical galaxies, they have this elliptical shape, looks like an oval shape, looks like a sphere that has been stretched along a certain direction, and we call those elliptical galaxies. And as we will see in this chapter, elliptical galaxies differ. They have properties different from those of spiral galaxies. And there's a different type of galaxies also called irregular galaxies. So what do you think irregular galaxies are? Well, if you said, well, irregular because they don't have a regular shape, that's a good one. So irregular galaxies, they do not show clearly indication of a central bulge and spiral arms. They don't have this nice smooth distribution of brightness so typical of elliptical galaxy, and they have all kind of a distinct shape. Some irregular galaxies, they appear to be the result of merge of spiral galaxies. Like when you see these two galaxies over here, you have in fact a merging process going on. There you go. But galaxies, irregular galaxies like Magellanic Clouds. Magellanic Clouds is an irregular galaxy. You can't see in the northern hemisphere. You have to go to the southern hemisphere to see it. But you can see with the naked eye. This is a picture of the large and small Magellanic Cloud. They appear in the sky with a naked eye. You don't need a telescope to see them, and they are this diffuse cloud. That's why Magellanic Clouds, but they are irregular galaxy. So irregular galaxies have also properties different from those of spiral galaxies and elliptical galaxies. Now, let's start with our own galaxy, our Milky Way. Our Milky Way is a spiral galaxy. Is this 25? Let me see. Yeah. So that is the galaxy we live. And again, when we studied the night sky in chapter 2, the concept of celestial sphere came by, and then I tried to mention back in those days, spiral celestial sphere really is not something that exists. I mean, it's a nice way we still use the concept of celestial sphere to indicate position of objects in the sky, but we are not surrounded by a bubble in which stars happen to be glued. Celestial sphere doesn't exist, and then I made a point that our solar system, is part of what we call Milky Way galaxy, and this chapter gives not only um, parts in which the Milky Way galaxy is made of. It described its central part that consists of a bulge and a central core region where astronomers found the presence of a supermassive black hole, about 4 million solar mass black hole, and also the spiral structures that are connected to the galactic bulge in our Milky Way, and also the halo that surrounds the entire Milky Way and the population of stars that happen to exist and happen to navigate through the galactic halo, HALO. And one of the less important topics in this chapter is the discussion about dark matter, which is the unseen, unaccounted, unseen, but an important component of our galactic halo. And so let's go through these different subjects. Now, William Herschel, and his sister, Caroline Herschel, they were important elements in the study of galaxy. He was the first one who attempted to provide a position for our solar system in the galaxy itself. So we understand the galaxy as being a group of several stars, right? And back in 1700, without the technology we have nowadays, now we keep saying, well, our galaxy has 300 billion stars, but that number was not dreamed of in the 1700s. And again, without telescopes, you can't see much far in space. But the existence of Milky Way galaxy, as you can see in this picture over here, see this fuzziness going across the sky? This is the Milky Way galaxy because we are inside this flattened structure where most of the stars are located. When I show you pictures, of spiral galaxies, like, for instance, take a look at this galaxy over here, that's Andromeda. So it has a bulge, which is the central part, has all these different spiral arms coming out of the bulge. If this galaxy were, it's not, but if it were the Milky Way galaxy, we would be somewhere 2/3 out of the center part of the Milky Way. So we were located somewhere here, okay, inside this spiral structure. So which means if you now can place yourself inside the plane of this galaxy, look around and look towards the sky, exactly what you see? Well, you see exactly this. You see exactly this. So looking towards, like now, if we were located where my hand to is, and if we look towards the center of the galaxy right here, right, then we would be looking towards one specific region in this stretch of gas or diffuse gas we see in the sky. And this diffuse gas is nothing but stars that are so far away, they clump together and they seem to be dust, sparking dust going across the sky. So Herschel, what he did some statistic work counting the number of stars in different positions of this Milky Way galaxy. So imagine now that you have this stretch of diffusive gas going across the sky from horizon to horizon. And then what he did, he counted the number of stars in different patches of the sky. And by doing so, and throughout the year, by the way, he was able to come up with a distribution of stars in the galaxy he could see. And by doing so, he predict based on his evidence, he predict that our solar system was in the center of the Milky Way galaxy. In other words, if you count the stars throughout the year in different positions, in different locations of this stretch of gas or diffuse nebula we call Milky Way galaxy that goes from horizon to horizon, we would count no matter which month and no matter which direction, we would count about the same number of stars. Like if you were in a forest surrounded by trees and you look around and you can count the same number of trees in any given direction, you would think that you were pretty much located and positioned at the center of this forest. And that's what he did. And this diagram here is an attempt to show his results. But later on, Harold Shapley, he did a different type of work using globular clusters, more particularly some variable stars called RR Lyrae that pulsate in globular clusters. They exist in globular clusters. They are stars. They are not in the main sequence anymore. They are low mass stars that happen to left the main sequence because of its hydrogen content in the core has been exhausted. And these stars have a consistent rate of pulsation in such a way that depending on the number of hours, and it has to be less than 1 day, of its pulsation, it directly relates to the luminosity of that star. And by measuring the brightness of these pulsating stars and using the inverse square law, then Harold Shapley was able to establish distance to the globular clusters he was investigating. Now, here in this black, kind of a blackish design is Harold Shapley. This black distribution of stars around the sun is portrayed here, in conjunction with the globular cluster Harold Shapley observed and mapped. So see, each one of these dots represents a globular cluster, which is a group of stars held together by gravitational force, containing more than dozens of thousands of stars. So the gravity, is very high. And what Harold Shapley concluded by positioning globular cluster in the galaxy, what he concluded was this: well, all these globular clusters are not going around our solar system. They are going around a region in the galaxy that's somewhere here. And since these globular clusters are massive objects, and since the center of mass of the galaxy should be the spot holding and connecting gravitationally to these globular clusters, he predicted the center of the galaxy should be somewhere here and not where the solar system was. And he was right, and he gained the right to have us talking about him, on a Monday night. So he was the first one who gave a strong evidence that our galaxy is extended. The center of the galaxy is about 30,000 light years away from where we are. So here is the central part of the galaxy. Our Milky Way is in What is indicated? Oh, it's not indicated. Oh, yes. So here's the center of the galaxy. Our sun, our solar system is somewhere at this location, 2/3 out of the way from the galactic center in a spur of Orion, Orion arms. It's right there. That's where the solar system is, and the distance from this point to the galactic center is about 30,000, 26,000 light years, but 30,000 light years just rounding up. Now the galaxy has also a thickness. If you think about the disk itself, when we studied star formation, we saw that the stars, the protostar is surrounded by a circumstellar disk that has some thickness. Same idea happened with when galaxies form. They have a center part where most of the material is accumulated, but the galactic disk is one where stars are still actively being formed, and where the giant molecular clouds we studied in our discussions happen to be gravitating and orbiting the galactic center. Now, the thickness of this goes from 2,000 light years to 400 light years. So the thickness of the galaxy is the galactic disk is significant if you think 2,000 light years, but the galaxy itself dimensions is 100,000 light years. So we think about the entire galaxy as being 100,000 light years. More on the Milky Way, and here is a nice display of what our galaxy should look like. So our galaxy should have a halo surround itself with globular clusters. These dots represent these globular clusters, which are old population of stars. Population 2 are considered old stars. They are giants, they are evolving. Population 1 stars are young stars. So the sun is considered a population 1 star. And population 3 were the first generation of stars ever formed, and we don't have them anymore in our galaxy. They are gone. But our galaxy has population 2 stars, the old stars in globular cluster. They have population 2 stars in the galactic bulge. See this bulge, this bluish coloration here, and population 1 stars primarily in the disk, and the sun is where located. Now, in the halo of the galaxy, we also accounted for the presence of dark matter. So dark matter, let's see if it can come up a little bit later. There you go. So dark matter is, we don't know what it is, and I think you guys presented a good argument in the discussion on the article. I think it was a extra credit reading material in an article about dark matter and dark energy. We don't know what dark matter is. There are candidates listed, and WIMP's weakly interactive massive particles is the most prominent candidate. Perhaps in our lifetime, we might hear some conclusive results on what dark matter is. But the main point is, if we take what we observe of our galaxy, the stars, the molecular clouds, the gas that happen to be located in the center part of the galaxy, if we take all together what we observe, what we detect, we would expect that stars beyond 15 kiloparsec. A kiloparsec is a unit of distance. Kilo is 1,000, parsec 3.2 light years. So 15 kiloparsecs, about 45,000 light years. Remember, our sun is about 30,000 light years. So the sun should be somewhere here, right? Our solar system. So we would expect that stars that are somewhat further out after 15 kiloparsec And because of Kepler's law, because of the Newton gravitational force that was discussed in chapter 3, we would expect the stars to go around the galactic center, and this is the so-called orbital velocity of the stars. We would expect them to fall down and to diminish. Like if you look in our solar system, Mercury goes around the sun rather faster than Jupiter, and Jupiter goes even faster than Uranus, right? So the farther the planet is, the slower, the less speed it takes to go around the center gravitational point of that system. And the same is true, or how holds true for stars going around the galactic center. So the further the stars are, um, the less speed they would take to go around the galactic center. And what astronomers observed was entirely different. So beyond that point, Newton's law breaks down. You don't observe what you're supposed to observe, and the orbital velocity of these further out stars, in fact, they go faster. And so how to explain that? So one way to explain that is uh, to assume in the galactic halo. Where's the galactic halo? There you go. See this galactic halo here? It's all populated by some unseen material all around in a sphere. All around the galactic halo is filled with this material. We don't know what it is, called dark matter, and by doing so, you can have the necessary pull that explains the fast orbital rotational velocity of these observed stars. So dark matter. But dark matter is not something newly proposed. It was proposed in 1930 by an astronomer named Zwick when he observed compact clusters of galaxies, and the galaxies were moving so fast, but he couldn't detect the material responsible for keeping these galaxies held in place. Based on their observed speed, they should flunk away. They should not stay in this compact group of galaxies. And then he was the first one proposing the existence of some material that was unseen, and it was termed dark matter. He was called crazy, but crazy he was not. And now we know he has his point. Now, our galaxy in the very center part, and the center of our galaxy is in the region Sagittarius, where the constellation Sagittarius is. In other words, if you go to the Starry Night software, and let's say go to November. And let's look at oh, wait a second. Oh, I knew something was wrong. Time is not right. Now is right. There you go. This is Scorpio, and So here's the constellation Scorpio. And you can see the Milky Way galaxy nicely going over this part of the sky. See the Milky Way galaxy. Imagine now you are inside the galaxy itself, looking towards this region over here, and this region is the center of the galaxy. So if we bring the constellation's name on it, that's Scorpio, and let me bring there you go. So that's the center of the galaxy, somewhere here in the region of Sagittarius. So the globular clusters that Sharpley was mentioning is orbiting all this region around. I wonder if Starry Night can show me where these globular clusters are. Let me see if I can bring them without getting myself lost here. Yeah, I have to look for, I'm not gonna go probably messy objects. Yeah, well, but anyway, so the center of the galaxies is in this region right here. And the center of the galaxy was found in part because of the detailed map of these massive stars. In fact, they are relatively young stars that orbit a point that are much smaller than it could be explained by the presence of some massive object like a superstar or a group of stars or whatever. And this object
Alert from System UI, sir.
Is so compact that can only be explained by the presence of a supermassive black hole of 4 million solar mass. So pretty much that's it for the Milky Way. My computer is gonna die in a second, but so let me know if you need anything, and I see you mañana.